we're going to be making what are called Cayley tables, which are essentially like multiplication tables from what, 4th, 5th grade or whatever. Except the operation is not necessarily going to be multiplication. It could be some sort of addition. And in fact, the main examples we'll start off with here just at the beginning, it is addition, but mod some number. We're going to have a set. Here's example 1 of integers. Now remember, z by itself represents all integers, positive, 0, and negative, infinite set. If I put a subscript down here, like maybe, for example, a 3, I'm not going to put a 3 right away, but if I did put a 3, that would represent a set of 3 integers. The first 3 integers where you start with 0, 0, 1, and 2, actually. Z3 as a set would be 0, 1, and 2. Z4 as a set would be the first 4 integers starting with 0, 0, 1, 2, and 3. Let's start even simpler. What about what's Z1? The first 1 integer starting with 0. In other words, Z1 as a set is just the set containing 0. This 1 element set is a group under addition. What kind of addition? Actually, you could do the addition, any kind of addition you wanted to. It's a trivial group. This is a trivial group because it's only got 1 element, and the group operation, in this case, say addition, whether it's regular addition or mod 2 or mod 3, it doesn't really matter, is essentially just saying 0 plus 0 equals 0. It's trivial. Its Cayley table is trivial. I put this 1 element at the top of the table here and at the side of the table there, and what goes here in the middle? Well, what goes there is 0 plus 0, 0. Very trivial. That is the trivial group. I am thinking of this as being the number 0, but it's such a weird trivial thing that we could denote it by any symbol that we wanted to. In general, the trivial group will be denoted by, well, an E as 1 element by itself. This is the general form of the trivial group. Is this the number E? No, it's not. In this class, E does not represent the number E unless we say so. So in general, it does not represent the number E. What does it represent? It represents the general abstract identity element. General abstract identity element. For this particular group, Z1, whose 1 element is 0, 0 is playing the role of E. This general abstract identity element in this general abstract trivial group, its Cayley table basically looks the same as the one with 0. E, well, here we think of this as 0 plus 0. We do think of the operation here as addition. Here we think of this E in here as E times E. I could put a dot for times. We don't typically bother with the dot. If I just write EE, it's assumed that means E times E, which you could write as 0 squared, or excuse me, E squared if you wanted to. If you're thinking of this abstract group in terms of multiplication, which we typically do as a traditional thing. When we're talking about group theory in the abstract, we typically imagine the operation to be multiplication, but for particular examples like this, it could be addition. Why use the letter E? It's a German thing. E is the first letter in, I believe it's Einheit. I'm actually not sure if that's a noun or an adjective. Nouns in Germans are always capitalized. I'm not remembering what this means exactly. So I'm not sure if it's a noun or not. Einheit, it's related to the number one, I think. Unit, that kind of thing is the basic meaning of that. Einheit. So that's the trivial group in two different forms. A particular form, you could call it a particular example, and an abstract form. What's the next level of complication? How about with two elements? Z2 would be the set of all integers, the first two integers starting with 0. As a set, it would contain 0 and 1. The group operation is addition, but it's not any old addition. It's not regular addition. That would be bad because if it were regular addition, 1 plus 1 would be 2, and 2 is not in the set, and the operation would not be closed. It would not satisfy closure. How about addition mod 2? 1 plus 1 mod 2 is 0. That works. That's closed. 0 plus 0 is also still 0. 0 plus 1 is 1, including in mod 2. So from this, I could create a Cayley table that's a little bit more complicated. The operation is addition mod 2. It's analogous to a multiplication table, but now it's an addition table. We are adding 0 plus 0. Yeah, that's 0. Even in mod 2, 0 plus 1 is 1. Mod 2 is still 1. 1 plus 0 is still 1. But 1 plus 1 does not equal 2. It equals 0. So in this group, under addition mod 2, you get to say weird things like 1 plus 1 equals 0. Do you have to say mod 2? Well, okay, if you want to for fun, mod 2. But you really don't actually have to, as long as you understand that you are working in this group, Z2. You also get to say things like -1 equals 1, mod 2, where -1 is not meant to be an element in this group in terms of a label, a basic label. It's meant to denote the additive inverse of 1. Additive inverse of 1. That's what the negative sign here is meant to denote in this context. I mean, yes, ultimately it is an element of this group. It's 1 itself. 1 is its own additive inverse because 1 plus 1 equals 0. That's the reason. But technically, when you put the negative sign in front of it, you're saying, I want the additive inverse of that thing. What's the abstract version of this? Abstract version. Call the group G. What should I label its elements with? Well, 0 is an identity still in Z2. What does it mean to be an identity? It means when you add 0 to anything, you get that anything. 0 plus itself is 0. 0 plus 1 is 1. It's called the additive identity. So we still want groups to have additive identities, or in the abstract version, multiplicative identities. Let's still have an element called E. What should the other element be called if it's got two elements? It doesn't really matter. Just pick something other than E. Usually people pick A. The Cayley table is going to essentially have the same form as the Cayley table for Z2. We see that E is the multiplicative identity. E times E is E. E times A is A. A times E is also A. This group operation is commutative. It's the identity. And what's the version of an additive inverse here? In the abstract, it would be a multiplicative inverse. A inverse is itself. Why? Because A times A squared, you can see from the Cayley table, equals E. You might wonder, does this spot in the Cayley table have to equal E? Does A squared have to equal E? Could it equal A itself? Could A squared equal A itself? Could it be, so this is our question, could it be the case? You know, am I forced to make this choice to put that E there in the lower right corner? Could it be the case that A squared equals A? Not in group theory, unless A happens to equal E, the identity. We'll see in ring theory later on in the semester, we do talk about groups, rings, and fields, like I say in the lectures. In ring theory, this can happen even when A is not the identity. There's two operations going on with ring theory, addition and multiplication. And the addition operation in a ring is a group, but the multiplication operation in general is not. But in group theory, this can't happen, because what if it did happen? There's a cancellation law. Essentially, the A's on the left here, if I write it like this, would cancel, and this would imply A equals E. But if I'm assuming A is not equal to E, that can't happen. I mean, this is a proof. This is essentially a proof that the only element of a group that's going to satisfy this equation is the identity. But you also have to prove that you can cancel, that there is a cancellation law, but that is the case in group theory. So you have to be careful. One tricky thing that happens in general with group theory is the operation's not necessarily commutative. So if I have a cancellation law, the general form of it might be something like this. If AB equals AC, the fact that the A's are both on the left is important to imply that B equals C. If I made that A on the left and this A on the right, this would not necessarily be true. It's kind of similar to matrix multiplication. Matrix multiplication is not necessarily commutative. And you have to pay attention to what side of the product a particular matrix is on. All right, let's keep going. Z3. The first three integers starting with 0, 0, 1, and 2. So the subscript specifies the number of elements. It also specifies the kind of addition modular arithmetic that you're doing. In this case, in the previous example was mod 2. In this case, it's going to be mod 3. Operation, the group operation, is addition mod 3. The Cayley table will have 0, 1, and 2 across the top and 0, 1, and 2 down the side. You were adding mod 3. 0 is still the identity. 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 2 is 2. Also, 1 plus 0 is 1, and 2 plus 0 is 2. Doing addition mod 3, addition mod 3. 1 plus 1 is 2. Mod 3 is still 2. 1 plus 1 is no longer 0 here. It's 2. And 2 is not equal to 0. 1 plus 2 is 3. Okay, I spoke too soon. Mod 3 is 0. I mean, okay, you can say that in your mind. 1 plus 2 is 3, but 3 mod 3 is 0. We're back to a 0 there. 2 plus 1 is 3, but 3 mod 3 is 0. 2 plus 2 is 4, but 4 mod 3 is 1. There's the Cayley table. Are we going to be making Cayley tables the entire semester? No. This is not the main point, but it is a good starting point. I mean, it will be helpful to make them sometimes, especially here at the beginning. But group theory is not really about making Cayley tables, at least as far as what people like to do. I mean, you could make it all about Cayley tables if you wanted to, but most people like to stop at some point and do something else. What would this be in the abstract? Again, you'd want an identity E, and how about an A and a B, I guess? What's the group operation? It's an abstract kind of multiplication. We're not really saying what it means. We're just looking for the same kind of pattern here with the elements. Essentially, E plays the role of 0, A plays the role of 1, and B plays the role of 2. And that gives the Cayley table essentially the same kind of structure. E plays the role of 0, A plays the role of 1, and B plays the role of 2. It's a similar structure. I'll call it a same kind of structure. I'll put the word structure in quotes. These groups, while they are different as sets and different in terms of the operation, and I'm not even really saying what the operation is here, other than the Cayley table essentially defining it. A squared is B, for example. A squared is B. A times B is E. B times A is also E. They have the same kind of structure. They are, the official name is isomorphic. Which is a word that basically means same form. Iso means same. Morph or morphic means form. Same kind of structure, same kind of form. In Z3, I could write things, yes, like 1 plus 2 equals 0. Mod 3. Therefore, the additive inverse of 1 is 2. Negative 1 equals 2, you could write. And you could also say negative 2 equals 1. The additive inverse of 2 is 1. Mod 3. Over here, it would look like A inverse equals B. It's perhaps best initially when thinking about these abstract groups to imagine that these letters represent matrices, just to have a concrete example in your mind. Perhaps matrices. But in this case, the matrix multiplication is commutative with this simple group here of 3 elements. B inverse is A. Yeah, A squared is B. A cubed, what would A cubed be? It would be A times A squared by definition. But A squared is B. This is AB. but AB is E. In other words, the inverse of A is A squared. But wait a minute, I thought the inverse of A is B. Well, yeah, but A squared equals B. It's a bit like going around in a circle. In fact, this is called a cyclic group. Feels like we're going around in circles. These things are called cyclic groups. Now you might wonder, is there any other way to make a Cayley table of 3 elements that will be somehow different than, say, this Cayley table in the abstract? Can I take these 3 arbitrary symbols, E, A, and B, and make a Cayley table that's somehow different from this? The answer is yes, but at the same time, no. It's both yes and no. What do I mean by that? Well, let's keep the meaning of E the same as the identity. What's to stop me from interchanging the roles of B and A? Other than the fact that A comes before B in alphabetical order. What's to stop me from doing that? Nothing really, other than just it feels weird. Although, you know, E comes after both A and B in alphabetical order anyway, so we've already been doing that. If I'm going to keep E to be the identity, then I'd have to fill in the Cayley table like this. And it would look different. But it would still have really, except for the roles of A and B swapped around, it would have the same kind of structure. Everywhere you see an A in the original table in red, there would be a B in the purple one. And everywhere you see a B in the original, there would be an A in the purple one. It really is isomorphic as well. These are isomorphic. In fact, isomorphism of groups is an equivalence relation. These 2 are isomorphic. These 2 are isomorphic. Therefore, these 2 are isomorphic. Well, yeah, I mean, kind of almost like, well, that's pretty obvious, wouldn't it be? That's transitive property of equivalence relations. They'd be in the same equivalence class if you considered the collection of all groups and the equivalence relation of being isomorphic. Group 1 is equivalent to group 2 if they're isomorphic as groups, if they have the same form, same structure to the Cayley table. And then the equivalence class of a group would be consist of all groups that are isomorphic to it. Which, since we're dealing with arbitrary kind of symbols here, you could argue there's infinitely many things I could write that would be isomorphic to these, because I could just use different symbols every time. That's kind of weird, but I suppose you could argue it's still one way you could think about it. Is there some other group with the 3 elements that's not isomorphic to any of these, that somehow has a different structure? The answer is no, not if you want it to satisfy the definition of a group, which I haven't officially written down. I've hinted at it. Mentioned identity elements and inverses. It's also got to satisfy closure. And it also has to satisfy the associative property. Let's do one more example. Up at one more time, Z4. First 4 integers starting with 0. So that'll be 0, 1, 2, and 3. Under addition mod 4 is what the group operation would be. 0, 1, 2, and 3 across the top and the side. This is a concrete group, meaning specific symbols with a specific kind of addition mod 4, not as abstract as it could be. 0 is still the identity. One plus one is 2. 1 plus 2 is indeed 3. 3 mod 4 is still 3. 1 plus 3 is 4, but 4 mod, I meant to say 3 mod 4 is still 3. 1 plus 3 is 4, but 4 mod 4 is 0. This group does satisfy the commutative property. 2 plus 1 is 3. 3 plus 1 is 0. The matrix, so to speak, that we're obtaining in the middle here of this Cayley table is a symmetric matrix when your group satisfies this commutative property. 2 plus 2 is 4, mod 4 is 0. 2 plus 3 is 5, mod 4 is 1. And 3 plus 3 is 6, mod 4 is 2. So in this group, you can write things like 1 plus 3 is 0. So the additive inverse of 1 is 3. Negative 1 equals 3 if you like. And the additive inverse of 3 is 1. 2 plus 2 is 0, mod 4. So the additive inverse of 2 is 2. Notice, by the way, if you did imagine these numbers as being on a number line, say an ordinary number line, interpreted in the ordinary way, and you plotted, for example, -1 and 3, 3 is 4 units to the right of -1, and 2 is 4 units to the right of -2. That's nice. Could I write an abstract version of this? Sure. E, A, B, and C, I won't bother. But the same kind of question that I asked a few minutes ago, does there exist some other group that's not isomorphic to this? When there were 3 elements to the group, I said the answer was no. With 4 elements, the answer is actually yes. Maybe I should write down the abstract version of a non-isomorphic group. So what I'm about to write down I could do this in such a way as to make it isomorphic, but I'm purposely going to make it non-isomorphic, to not have the same structure. E is still the identity. But the way I'm going to start making this different in structure from this table is I'm going to make, in this group, this abstract group, every element its own inverse under multiplication. So A squared, for example, is going to be E. B squared is going to be E, and C squared is going to be E. All E's down the main diagonal. That didn't happen over here. Not all zeros down the main diagonal. There's still a question, can I define the other products in such a way that it will be a group? The choices that are left for these final 6 boxes are not, they're not arbitrary. I can't just put any letters that I want in any order that I want. I have to do it in a specific way. And the way it turns out you want to do it is put a C here and a B here, then a C here and a B here. It is still going to be satisfy the commutative property. Finally, in these 2 spots, put A's. Notice when I do this, in the main body of the table where the answers are, in every row and in every column, each letter occurs just once. Kind of like Sudoku, I guess, with letters, a smaller table. They occur just once. That has to happen if it's going to satisfy the properties of a group.